In chapter one, we began to sort out some terminology and vocabulary so that we could begin to talk with a common language when it came to collecting and data and talking about data in specific ways. In chapter two, we make an important shift. One of the things that is critical when it comes to statistics is we want to be able to find ways to give visual descriptions of our data. But we want to make sure that our visual descriptions communicate what the data actually says. And so we're going to set up for ourselves some techniques and some ideas that help in that process. How do we organize data so that we can visually communicate it to the individuals that we are trying to communicate to? Because in a lot of ways, the old saying goes, a picture says 1,000 words, right? In that a picture can communicate much more efficiently and effectively to the average person rather than just looking at raw data. So section 2.1, we're going to begin the process of organizing our data so that we can construct efficient and visual representations of our data that communicate effectively. So let's take a look at this idea of what is called a frequency distribution. It's the organization of raw data in table form using classes and frequencies. Okay? So here's what we mean. I've got a set of raw data. I don't know what the data represents. That doesn't matter for this example as we learn how to construct a frequency distribution. What matters is this. When I look at this grid of numbers here, it's really hard to make sense of anything. Right? The average person looking at that grid of numbers is just going to look at it, stare at it for a second and go, I give up, I'm walking away. Can we organize it, though, in a way that allows us to quickly communicate what the data is actually saying? And the answer is yes. And we start that process by constructing these things called frequency distributions. So what we have here down in this table right here is a frequency distribution. The question is, how did we get from this to that? We got from this raw data to this frequency distribution utilizing two concepts, the concept of a class and the concept of frequency. Let's take a look at class first. Taking a look at this first column titled class limits, we want to determine how did they get from this raw data to these class limits. So here's how they did that. In this data, let's go ahead and find our smallest, I think it's the 27 right here, and our largest data values, the 92 conveniently right above it. There's a 91 down here, but 92 is definitely bigger. So we have our smallest and we have our largest data values. Okay. What we're going to do with this is we're going to find the difference between those two. So I'm going to do 92 minus 27. And if I do that, I get 65. Okay. Now, we want to determine how many what we're calling classes do we want to break our data up into. The people that did this example chose, 1, 2, 3, 4, 5, 6, 7, 8. 8 different classes, and each class represents a range of the data that we collected. So what we're going to do is we're going to take this 65 and we're going to divide it by 8. And that ends up being 8.125. Now, it's not convenient to have a class width that is a decimal. So what we always do is we take that number and we round it up to a 9. What does that 9 represent? That represents the difference or how much of our data fits into each class. Here's what I want you to notice. In this class limit, we started with our smallest value, 27. What did we then do? We added 9 to it. 27 plus 9 is 36. 36 plus 9 is 45. 45 plus 9 is 54. 54 plus 9 is 63. Plus 9 is 72, plus 9 is 81, plus 9 is 90. So we are going to call those our lower class limits. So our first class right here is 27. The next class starts at 36, which means the class before it actually ends at 35. Okay? So this value that we got by finding the largest minus the smallest and then dividing it by how many classes we wanted and then rounding it up, this gives us the values of all of our lower limits. The upper limits are just the value one less than the lower limit of the class above it. So we have all of our classes now defined. So what we're going to do is we're going to say we want to take a look at all of the values in our raw data right here and how many values. I don't care about what the value actually is. I just care how many of them are 27 through 35. And what we find out is, you'll see here they make tally marks. They only found one. Okay? So they made one mark. Now we're going to look at 36 up to 44. So if I scan through this 36 up to 44, here's a 44, here's a 38, and here is a 38. And I don't think anything else is between the 36 and the 44. So look at what they did. They made 3 tally marks right here. They're going to continue that process for each of these classes here and make those tally marks. And then what they're going to do is they're going to write out just the value of how many tally marks there are. So you can see in this first class, there's 1 tally mark, then 3, then 9, then 15, then 10, then 3, then 7, and then 2. And here's the key. All of these values right here should add up to the total number of data points. And sure enough, it does. These values over here are what we call frequency. The frequency of a class then is the number of data values contained in a specific class. Makes sense why we use the word frequency. Frequency implies how often. Right? So how often in our data set does a value come up that fits within a class? So we constructed a frequency distribution. And so those are the concepts behind it. We break up our raw data into classes, and then we simply go through and figure out how many data points fit into each of those classes. Now in this example, we had quantitative data, data that had a specific numerical value. What about data that doesn't have a specific numerical value? Okay. Qualitative data. Well, qualitative data can fit into this category, what we're going to call categorical frequency distributions. The categorical frequency distribution is used for data that can be placed in specific categories, such as nominal or ordinal. We took a look at those vocabulary words in a previous section. For example, data such as political affiliation, religious affiliation, or major field of study would use categorical frequency distribution. The example we have here actually uses blood type. So they randomly selected, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks like there's 25 total subjects here that their blood type was tested and recorded. Well, it would be nice to organize this in a way where the data is useful or easier to see. So again, the first step in doing that, in organizing our data, is through these things called frequency distributions. And you're probably catching on already, what are we going to end up doing here? Well, it's a lot easier to define your classes with categorical data because each category becomes your class. So we have type A blood, type B blood, type O blood, type AB blood. So what we're going to do is we're going to go through, let's look at A. I've got 1, 2, 3, 4, 5. I'm going to tally them, 1, 2, 3, 4, 5. Okay, I have 5 total blood types of type A. So my frequency for the A class is 5. I'm going to go through and do that with B's now. 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4, 5, 6, 7. Our frequency for blood type B is 7. If we go through this, what we're going to find out is the frequency for O type is 9. Well, let's just do that really quick. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, and 9. There's your 9 right there. Okay, tally those off. And last but not least, we have the least common blood type out there of AB. And we've got 1, 2, 3, and 4. So 1, 2, 3, 4. Blood type of 4, or sorry, a frequency of 4 for blood type AB. Great. So we found the frequency in each of our classes. The classes were just the categories that we had for our categorical data. Notice this last column, though. This is another step that is important, especially as we get into chapter 2.2 and start constructing different visual displays of data. It's important to find what percentage of the data fits into each of these classes. Well, 5 and 7 is 12, plus 9 is 21, plus 4 is 25. Oh, that's what we said. We had 25 total data points. Well, what we want to do is we want to ask ourselves, okay, 5 out of 25 is what percentage? Well, if you do 5 out of 25, that gives you a decimal, right? 5 divided by 25, it gives you a decimal of 0.2, right? Well, percentage-wise, that's 20%. If we do 7 divided by 25, we're going to find out it's about it's going to be 0.28-ish, so 28%. And if we take our 9 and divide it by 25, these can all be looked at as fractions as well. 5 out of 25, 7 out of 25, this would be 9 out of 25. What we end up with is 0.36, so 36%. And lastly, 4 out of 25, or 4 over 25, you end up with 0.16, so 16%. And if you add these percentages up, what you're going to find is they all add up to 100%. Okay? So sometimes what we're going to find is we actually want to find out the frequency, what percentage that is of the whole. Wonderful. Well, we have one final thing to look at that defines a few more things when it comes to frequency distributions. In this last example, it says this: when the range of the data is large, the data must be grouped into classes. We've already seen that. That's what we did in the first example, that are more than 1 unit in width. Right? We saw that as well in what is called a grouped frequency distribution. So here's the key difference between the first example and this example that we're now looking at is, it says this: for example, a distribution of the blood glucose levels in milligrams per deciliter. In the original data, the first problem that we looked at, all of our data values were whole numbers, right? There was no fractions. Everything took on a whole number value. But in this example, is it possible to have a milligrams per deciliter that is some fraction or decimal between two whole values? And the answer to that is yes. So the question is, how do we handle that scenario? And it's actually going to go back to something we looked at in chapter 1. Let's take a look at that really quick. So what they did is, we're not looking at any of the raw data. We're actually looking at the result that they got for the frequency distribution they put together. What they found was the lowest value was 58. And then the highest value is somewhere up here between 100 and 106. And they decided that they wanted 1, 2, 3, 4, 5, 6, 7 different classes. Okay? So in those 7 classes, they took the max minus the min to define how wide the class should be. Okay? And In that, then, they were able to identify what we're calling lower class limits and upper class limits. If I take a look at this first class right here, what is my lower class limit? Okay. Well, my lower class limit is simply the lowest value defined in that class. So 58 would be my lower class limit. What is my upper class limit? Well, it's the top end of the class. 58 up to 64, 64 being my upper class limit. So every class width has upper and lower class limits. Fairly straightforward, fairly easy to understand, right? But here's the thing, here's the problem. Okay? We know that a value could take on a value somewhere between 64 and 65. How do we handle that? That's where we come up with these things called class boundaries. So you'll notice this second column right here gives class boundaries. It says this. What we're going to do is we're going to look at the upper class limit and the lower class limit of two adjacent classes. And we know it jumps from 64 up to 65. Well, let's find the middle of those two, halfway between, and that's going to be the boundary. So take a look at what they've done here. They've actually added and subtracted a half from both my lower and upper class limits. So my class boundaries are 57.5 up to 64.5. So if I have a 64.3, this helps me identify that that actually fits here. But what if I had a 64.8? Well, that helps me identify it actually goes in the next class up. So our class boundaries define for us it defines for us where values between lower and upper class limits end up. So they defined the rest of their class boundaries, and then what they did was they found out how many data values fit into each of those class boundaries. They tallied those up, and here are the numerical values that give you the frequency in each of our classes for a total of 50 data values. Now, the last thing that we need to consider here is this concept called class width. Now, it would be tempting to say, well, my class width is just the distance from my lower to my upper class limit. If I were to do that, the distance from 58 up to 64 is 6. Right? However, what we actually need to be doing is a class width is actually not defined by the class limits. It's actually defined by the class boundaries. But there's a really quick and easy way without having to look at boundaries to find your class limit. Your class width. To find that, simply take the lower class limits of two adjacent classes and find the distance between those two. So 58 up to 65, that's actually 7. So my class width here would be 7, not 6. And you'll notice that that class width stays constant. 65 plus 7 is 72. 72 plus 7 is 79. 79 plus 7, 86. And you see the pattern as it continues. So frequency distributions, what they do for us is they organize data in a convenient way where we're now in section 2.2 and 2.3 going to be able to take these frequency distributions and turn them into visual displays that help us effectively and accurately communicate the data to the individuals who need to see it.